Mind your decisions, I'm Presh Talwalkar. A circular sector can be folded into the shape of a three-dimensional cone by joining its two radii together. The exact size of the cone will depend on the size of the circular sector. Let's unroll this cone back into a circular sector. Suppose that we have a fixed radius of this circular sector and we just vary the central angle of this circular sector. What will happen to the cone? Naturally, the cone will change in size. It will go from tall and narrow to very long and wide until it flattens into a circle. Each of these circular sectors corresponds to a different size of the cone. The question will be the following. If we have a circular sector whose radius is equal to 1 and central angle is equal to theta, what is the maximum volume of the cone that's possible? Part 2. Solve for theta when the cone's volume is a maximum. I thank Joe for this suggestion. Pause the video if you'd like to give this problem a try, and when you're ready, keep watching to learn how to solve this problem. The dimensions of the circular sector will determine the size of the cone. The radius of the circular sector will be equal to the slant height of the cone. Since the radius is equal to 1, the slant height is equal to 1. We then have the arc length of the circular sector will be equal to the circumference of the base of the cone. The size of the arc length is equal to its radius multiplied by the central angle. In this case, we have 1 multiplied by theta, which will be equal to theta. Therefore, the circumference of the base of the cone will also be equal to theta. Now focus on just the cone. We'll label the radius of the base as r and the height of the cone as h. We have a right triangle formed between the radius, the height, and the slant height. We can thus use the Gogu theorem to determine that r squared plus h squared is equal to 1 squared. We then solve this equation for r squared. From here, we will go to the formula for the volume of a cone. It'll be equal to 1/3 pi r squared h. Since we know what r squared is equal to, we'll substitute that into the formula, and then we'll simplify. We thus have a formula for the volume in terms of just one variable h. We'll thus take the first derivative with respect to h, and we'll set it equal to 0 to solve for the maximum volume. We'll solve this equation very easily to get that h is equal to 1 divided by the square root of 3. Just for fun, we can double check that this is a local maximum. We then substitute the value for h into the volume formula, and we get the maximum volume is equal to 2 pi divided by 9 times the square root of 3. From here, we need to calculate the central angle theta, which gives us maximum volume. To do that, we'll solve for the radius. Using this formula, we'll solve for r, and then we'll substitute in for h. We get that r is equal to the square root of 2/3. Then we consider the circumference of the base of the cone. The circumference is equal to theta, and it's also equal to 2 pi r. We substitute in for r, and we thus have the value of theta in radians. We multiply this equation by 180 over pi to get the answer in degrees, and that's approximately equal to 293.9 degrees. And that's our answer. This is a fun optimization problem, and the answer works out very nicely. Thanks for making Mind Your Decisions one of the best channels on YouTube. As always, thanks for watching, and thanks for your support.